he has given couple of uniqueness theorem here. Again, there are many uniqueness theorem. He collected couple of them. I think we don't have to prove them. Okay, let me just solve some problem. That's sufficient. But mathematically, when we proceed in the theory, those should be stated. Is that okay? Those should be proved. Is that okay? Again, I told these all are mathematical evolution. Okay, of earlier one. So now, so write down uniqueness theorem. First uniqueness theorem. These are mathematical statements. We can prove that one. The solution to Laplace equation. The solution to Laplace's equation. The solution to Laplace equation in some volume V. In some volume V. Is uniquely determined. Is uniquely determined. Is uniquely determined if V is specified on the boundary surface. If V means potential, if potential is specified on the boundary surface of the volume. Okay, what is the main theme? I have some volume. Okay, I have some volume. So now, if V is specified on the surface, this is the surface of the volume. If V is specified, then you can find potential uniquely inside. Is it okay? So potential inside that volume, inside that region, you can find it uniquely. We shall have an example. Okay. Again, you can't remember that theorem for a long time, but you can remember this example. Okay. Now I have a enclosure. Okay. I have an enclosure. He's saying show that potential is constant inside an enclosure completely surrounded by a conducting material. Okay. I have some region where this coating is conductor. Shall I say like that? That may be so any region, or that may be empty surface. The surface is conductor. Let me take inside. Inside you can take it as a conductor. If you take conductor, it is equipotential. Potential is constant. Is that okay? Now let me take assumption like this. This is a metal closed surface, closed metallic surface. Is that okay? Once it is closed metallic surface, so potential, if potential is V0 on the surface, it is same. So throughout the surface, am I right? Because conductors are equipotential. Is that okay? Now let me take surface which is made of closed surface which is made of metal. Is that okay? Inside let me take empty space. Okay, inside that region let me take empty space. There are no other charges inside. Okay, no charges inside. And this is what you call conducting surface. Okay, the surface is which is made of conductor. A kind of thin sheet, you can just imagine like that. Since potential is uniform, since potential is constant, so over all that surface, look at here, and inside there is no charge. Inside del square V should be equal to 0. Am I right? If del square V equal to 0, then V suffers no local maxima or minima, isn't it? So potential is constant throughout the surface, and potential should not have maxima or minima inside the region. Then potential should be same everywhere inside. There is no other choice. Are you getting my point? Potential is same at all points on the surface. Okay, and inside the region, Laplace equation is satisfied. If Laplace equation is satisfied, potential should not have any local maxima or minima. So that's why the potential inside should be same as the potential at the boundary. Is that okay? Why? Look at here. Suppose here I have potential V naught. So when you end at other surface, other side of the surface, again you should get potential V naught because it's a conductor. Let me imagine like that. Okay. So now, if suppose your potential is increased, suppose you are traveling from here to here. So through the inside region, is that okay? Suppose your potential is increased, then it should have decreased, isn't it? If potential increases when you go inside, it should decrease to V naught when you reach other side. If it increases, then there will be some maximum. Suppose when you start your journey from here to here, suppose potential decreased by, from V naught when you go inside, and that potential should increase because at the other end it should again attain V naught, isn't it? Then there will be minimum inside the region. That kind of thing cannot happen. So that's why potential should be constant throughout the inside region, so as long as there is no charge. Yeah, the question, quickly. Potential is constant inside an enclosure completely surrounded by conducting material. Can you write? Potential is constant inside an enclosure completely surrounded by conducting material, provided there is no charge within the enclosure. Provided there is no charge within the enclosure. Is that okay? Video watching? Stuck up. Okay, frame per second. Only while I'm moving. Should not move. Okay. On the walls of this, suppose let me take it as a cavity. On the walls of the cavity is conductor. So then obviously throughout that walls of the cavity, potential should be constant. That's why it should be constant inside. No other charges inside. It should not attain maximum or minima inside because Laplace equation is satisfied. You can argue like that. Is that okay? We had one example. Do you remember? We have already taken this one. Suppose charge Q is uniformly distributed over the surface. No need to be conductor. Am I right? So, do you know we found what is the potential on the surface when you go from infinity to R? Am I right? Suppose R is the radius of this one. Potential on the surface, what was this one? 1 by 4 pi epsilon naught Q by R, I think. Isn't it? From wherever you go, look at here, potential on the surface, on this spherical surface, that is same. Isn't it? If potential is same, so throughout the spherical surface, and there are no charges inside, only charge is uniformly distributed over the surface. That's what we have taken. Okay, spherical shell problem. In that case, potential on the surface was constant and potential inside was same as potential on the boundary. Is that okay? Now you don't have to think over it. You have to quickly write what is the potential inside? 1 by 4 pi epsilon naught Q by R. Should be constant. Is that okay? Obviously, electric field is 0. Okay, electric field is 0. Yeah. So now, suppose if we talk about field inside a cavity, this kind of cavity, which is surrounded by a conductor, definitely that field will be 0. So that's kind of Faraday cage. Field will be 0. So because potential is constant, whenever potential is constant, gradient equal to 0. Is that okay? Gradient of constant equal to 0. Yeah, so he has written one second uniqueness theorem. Just take that one later, okay? Have a note on the second uniqueness theorem. Yeah, but I need to take one more example here. Yeah, write down second uniqueness theorem. Second uniqueness theorem. In a volume V, capital V. So write V in a little like this, okay? Because ordinary way we use for potential, okay? In a volume V, surrounded by conductors and containing a specified charge density rho, comma, the electric field is uniquely determined. If total charge on each conductor is given. Now he has given one example, okay, but I couldn't 100% what you call. I couldn't link that one with the uniqueness theorem. First uniqueness theorem, you have that one. You have that definition. Once potential is specified on the boundary, so potential uniquely determined inside the region. Okay. Now look at here. So I have these charges. Okay, plus Q here, minus Q here. These are small what you call metallic balls. So take like that. Okay. So a plus Q, minus Q, and here minus Q, plus Q. Okay, these are metal or so metal what you call balls, and you have plus Q, minus Q, minus Q, plus Q. Okay. Now what I do here is I am going to connect these two by a conducting wire. I am going to connect these two by a conducting wire. Okay, what is the configuration? Whether those charges will remain over there or whether they neutralize, because there exists the electrostatic attraction, isn't it? What is the configuration after you connect them by a conducting wire? Yeah. Will they be like that? Yeah. Will they neutralize or not? This also, that's why I have taken that as a conducting sphere. So that when you connect, I mean, if it is insulator, in insulator charges are localized actually. They are not free to move. So they are not allowed to move. Okay. But I have taken conducting spheres, they are charged like that. Now I am going to connect them by a wire like this. Will it neutralize or will it be like this? Because there exists an attractive force between them, am I right? It will be neutralized. Now we need reason. Now look at here. Now just read the uniqueness theorem. If total charge on each conductor is Q1, then if total charge on each conductor is given, then electric field can be uniquely determined, isn't it? What is the total charge on this one? Now this becomes the same conductor. What is the total charge on this one? 0. That's why electric field is 0. Is that okay? So that's why the configuration is this one. No charge here. 0 charge here. Quickly they will neutralize themselves. It's very difficult to argue, but uniqueness theorem says like this. And you have proof. Is that okay? The configuration after you connect them via wire, conducting wire, it will be like this. Because the only possible way of distributing 0 charge on the conductor, you have given, so suppose plus Q charge as well as minus Q charge. You have given plus Q charge, minus Q charge, and you are allowed to distribute them on the conductor. How do you distribute? 0 again. So 0 charge, isn't it? So because charges are free to move out there. Is that okay? So whenever total charge on the conductor is uniquely mentioned, so whenever, what is the sentence? Total charge on each conductor is given, electric field is uniquely determined, isn't it? So if you keep this configuration, you will have electric field, isn't it? So it will be this configuration and there will be no electric field. Is that okay? So just think over it, this example, they may design question. Again, I can go for image problems, the time 8:25. Now, until now, look at here, we haven't touched that del square V equal to 0, isn't it? I told this whole chapter is a potential formalism. Potential formalism is solving either Laplace equation or Poisson's equation. Isn't it? We have two equations, del square V equal to minus rho by epsilon naught. So, in the region where rho equal to 0, what would happen? Del square V equal to 0. Okay, or we haven't touched that one. Still, we are trying to escape from that one because that's not that easy, isn't it? You have to separate the variable and you have to do that one. Okay, we will do that one. So, in the next part. So, again, we have one more idea here, the method of images. I hope we have studied method of images, isn't it? So what is this method of image? This can be applied in many cases, okay? This can be applied in many cases, and again, it's a kind of avoiding Laplace equation, Laplace or Poisson's equation, again using boundary condition and uniqueness theorem. So solving this one actually, okay? So theoretically. So, but it's a kind of technique actually. Okay, let me take an example. Suppose a point charge Q held at a distance d above the infinite plane which is made of conductor. Okay, let me discuss part of this one, okay, because it's little important topic. Okay, I have infinite plane, infinite conducting plane. I feel little difficulty in saying like that, isn't it? Conductance is not, yeah, obviously pure conductor. Conductance is infinite, am I right? Resistivity is 0. Conductivity will be infinite. Yeah, whatever. It's an infinite plane made of conductor. Is that okay? And again, it was not charged initially. Okay, it was not charged initially. You are going to put a charge plus Q. You are going to put a charge plus Q. So at a distance d above this one. At a distance d above the plane. Okay, that conductor is on xy plane. Okay, infinite sheet. And what I do here is I am going to maintain this one at 0 potential. And you can ask question. I can choose that one as a 0 potential. Potential formalism doesn't have unique definition. Is that okay? I can choose that one as a zero potential. Somewhere after outside, he has given some ideas like that. Okay, suppose that is not grounded. So in most of the example, they will give grounded, infinite grounded conducting plane. He said infinite grounded conducting plane. Grounded means potential is zero throughout the plane. Is that okay? If it is grounded means ground means zero potential. Is that okay? So infinite grounded conducting plane, a charge q is held at a distance d above. Is that okay? So now question, what is the potential in the region above the plane? Okay, what is the potential above the plane? Means z greater than 0. Now again the question, why we can't talk about below the plane? Because we don't know what is happening below the plane. Whenever you have infinite conductor like this, so below region will be completely obstructed by above region, or above region is completely obstructed by the below region. Remember, it's a kind of shielding. Again, your Faraday cage kind of thing. Why it is extending to infinity? In Faraday cage, you will make it closer, am I right? But now here you are extending that one to infinity. That means you are completely, you can't see what is happening below, remember. And it doesn't matter. And it doesn't matter. Why? So you know what is the potential in this boundary. Right? And when you go to infinity, when you go to z to infinity, then also you are escaping from charge distribution. Definitely. So potential at z equal to infinity, that's also 0. You know the potential at the boundary. Our uniqueness theorem says, again, combiningly those two uniqueness theorem, the potential at the boundary is known. So charges are known. You can find potential uniquely. But again, we are not going to solve the differential equation. We are going to take a different method. That is the image problem. That is the so technique, a kind of technique. Are you getting the situation? Situation is an infinite plane which is made of conductor and it is grounded. Potential on that one is 0. Okay, and our aim is to find potential above the plane. Remember, above the plane. So suppose if there are no charges below the plane, what is the potential below the plane? Why 0? If there is no charge below the plane, what is the potential below the plane? Plane is grounded, okay, conducting plane. What is 0? Now look at here, if there is no charge here, so throughout this plane, xy plane, potential, that is a boundary, am I right? Throughout that plane, potential is 0. Again, potential is 0 at z equal to minus infinity. Potential is 0 everywhere throughout the boundary. And there are no charges inside. Potential should not suffer any maxima or minima. That's why potential is 0 everywhere below. But we are not talking about below plane here. Is that okay? If they ask any question on that one, write it 0. If they ask what is the electric field below the plane, or what is the potential below the plane, write it as 0. I mean, if there is no charge. But our aim is to find potential above the plane in this problem. Okay? So we can't talk about below the plane. Now look at here. Obviously, this plus q charge, it will induce charges here, definitely. Yeah, you can place that one. Then below region you have to take separately, above region you have to take separately. They are very independent because of that conductor. And it is again 0 potential. Is that okay? Because of that conductor. That's why I said below region is completely obstructed. Like that, okay? Now look at here. There will be plus q charge, am I right? Plus q charge. So again it will induce charges on the surface of the conductor, am I right? It will induce charges on the surface of the conductor. But the problem is we don't know what is that surface charge is. So if you know that surface charge density, we can use our electric to find electric field or potential. We can find electric field, we can find potential, we can do something, or at least we can do some calculation, isn't it? That is not now. isn't it? The induced charge density or distribution, that is not known here. Is it okay? That's why we want to have some technique to solve this one. What is the technique? So technique of taking image, look at here. I hope this was there in BSc, right? So you placed a plus Q charge at a distance d above. Now what you do here is, remove the plane. Don't keep that one. Remove the plane and place minus Q charge below that one. Is that okay? Now this configuration will make XY plane zero potential. If you are in XY plane, this is along minus Z cap, okay? This is along minus Z cap. Can you just imagine? If you take any point on XY plane that is equidistant from plus Q and minus Q. Can you imagine? Because XY plane is the middle one, am I right? XY plane is cutting the Z axis at the middle. So if you take any point on XY plane, that will be at zero potential. Potential due to this one, potential due to this one, am I right? 1 by 4 phi epsilon naught plus Q by distance from plus Q, okay? Plus minus Q divided by distance from minus Q. These two will be same if you take any point on XY plane. Is that okay? So now these two configuration have the same boundary condition above the plane. Again, I can't talk about below the plane. If you are just concentrating above the plane, okay, XY plane is zero potential. Look at here, above I have one charge and potential at infinity is 0. Okay, XY plane is zero potential. Above I have one charge, potential at infinity is 0. Above plane is equivalent in both of these ones. So above the XY plane, the region above the XY plane is exactly same in both two configurations. And that's what we need. We need potential above the plane. That is the problem. Below the plane, these two are not equivalent. Why? You have no charge here, you have charge over there. They will ask this problem, not that problem. Don't get confusion. Is that okay? That is, so this is the image configuration. We call this one as image configuration, where above the XY plane, so boundary conditions are same. That's why potential should be unique. So potential should be same. Is that okay? So now look at here. So in the mathematical point of view, look at here. V equal to 0 when Z equal to 0. Am I right? Just let me see these two. For Z greater than 0. Okay, let me just see what is happening Z greater than 0 here. V equal to 0 when Z equal to 0. Am I right? And V tends to 0. V tends to 0 when you move very far away. Suppose V tends to 0 far from the charge. Or x square plus y square plus z square under root, that is very much greater than d. I mean, d means the distance between a plane and charge when you are very far away. When you are very far away, or you can say r tends to infinity. From the origin, if you are going to infinity, then obviously potential should go to 0. That means you are escaping from charge distribution. So remember, even though the induction happens on the surface, that induced charge should decrease when you go to infinity, even on the plane. No need to worry. Is that okay? It's not infinite charge distribution. It will never happen. Okay, it's finite charge distribution. So that's why when you go to infinity, so let me say like that, when r tends to infinity, you are escaping from charge distribution, it is 0. The same thing will happen here also. So just concentrate above the plane, okay? Because our interest is to find potential above the plane, okay? So now, what is so potential V equal to 0 at Z equal to 0? Because z equal to 0 means xy plane. Xy plane is at equidistant from these two charges. Potential due to them cancel out with each other. And v tends to 0 as r tends to infinity. R means distance from the origin. You can take like that. Okay, this is the origin. This is the origin of our coordinate. Now, these two have the same boundary condition. That's why whatever the potential you find here, that is same as potential finding here. Isn't it? In this one, we don't know what is the surface charge, induction. So, induced surface charge, we can't find easily. But here, we don't have any induced charge, but it will give the same boundary condition. We can find a potential very easily. Am I right? So, now what is this distance? So, what is this point actually? 0, 0, d. Can I write like this? What is this point? 0, 0, minus d. Is that okay? So, now take any point above the plane like this, okay? X, y, z, okay? Take any arbitrary point. What is the potential at x, y, z? Now, you need distance from these charges. Okay, let me take distance from plus q charge as r plus, distance from minus q charge as r minus, 1 by 4 phi epsilon naught. So, plus q by r plus minus q by r minus, where r plus and r minus are distance between these two and these two. Are you getting the technique? Technique is to avoid our Poisson's equation or Laplace equation, remember. Okay, technique is to have the configuration which gives the same boundary condition. So now what is the potential? 1 by 4 phi epsilon naught q divided by what is r plus? R plus is the distance between these two. Isn't it? What is the distance? X minus x square plus y square plus z minus d the whole square. Under root. That is r. What is r minus? X square, x minus 0 the whole square, y minus 0 the whole square, z minus of minus d the whole square. Okay? So, x square plus y square plus z plus d the whole square under root. What is this one? This is potential when z is greater than 0. Don't forget. And in one JEST exam, they have given this configuration. They asked what is the electric field below. What is the electric field at somewhere here at this point below. What will you do? Will you take image configuration and find the resultant electric field? No, that is not the situation. Situation is this one. Is that okay? Situation is this one. Electric field should be 0 because it will shield that one. It will shield below region. Okay. So they may design question so that whether you know that concept or not, why we do this one like that. Is that okay? This is the potential only above that one. We can't talk about below region, and below region is not of our interest actually in actual problem. Okay. Now you can put z equal to 0. When you put z equal to 0, these two become same. You will get 0. Isn't it? When you put z equal to 0, x square plus y square plus d square, x square plus y square plus d square. You will get 0, obviously. That should happen. Again, when you take this denominator very high, when you go to infinity, this will be very high. Obviously, denominator factor increasing and it will be 0. Okay, it is satisfying those two conditions. Is that okay? So now this potential is, again, we found this potential by looking at this configuration. We call it as image configuration. But the same answer follows here. That is the idea. Trick. So you don't know how this surface charge distributes over the surface. Isn't it? There will be more induction nearby the surface. Okay? There will be more induction nearby the surface because that surface is nearby this plus q charge. that induction is low when you go outward from the surface. Okay, so that's why you don't know what is that charge distribution, then you can't go for any of our earlier formula. Okay, to solve it, you don't know charge distribution. If charge density is specified on the conductor, again second uniqueness theorem says you can find the electric field uniquely. But that charge density is not specified here, or it cannot be known that easily. So that's why we follow that image method. Is that okay? Yeah, speak out. Now, can you do some calculations? He has given induced surface charge. Now, how do you find induced surface charge? You know potential above, am I right? You know potential above. You can find electric field above. Isn't it? What is the electric field below? It should be 0. You have a surface charge means electric field should suffer discontinuity. You can use that discontinuity to find the surface charge, am I right? So I think a couple of class before I told we are going to use one formula to find the surface charge, am I right? Now look at here, potential is equal to this value above the surface, okay? Potential equal to 0 below the surface. Can I take so can I take like that? Again, what was the argument? Below surface, below there are no charges, and surface is 0 potential, and at infinity again potential should be 0. That's why it should be 0 throughout the region below. It should suffer no maxima or minima. Laplace equation is satisfied. Is that okay? That's why what I do here is V equal to 0 below. Okay, V equal to this value above. Is that okay? So now I told something. Dou V above by dou n minus below by dou n is equal to minus sigma by epsilon naught, where n is any variable perpendicular to the surface, and that derivative should be taken on the surface. That was our boundary condition. That's again discontinuity of perpendicular component of electric field. Perpendicular component means that derivative, isn't it? That derivative of the potential. Is that okay? So we have taken this one, am I right? A kind of directional derivative, isn't it? It's a kind of directional derivative of the potential. Okay? Now, what is the plane which containing charges, surface charges? That is this plane, xy plane, isn't it? So now, if it contains charge, again, so you can take this one, you can use this one to find surface charge density, because now you know what is the potential above. And now I argued what is the potential below. Below potential you can take it as 0. You know what is the potential here, what is the potential here, you can take derivative discontinuity. Obviously potential is 0, derivative is 0. Okay. Now what is the derivative? Derivative with respect to Z, because now Z is normal to the surface. What was n? I said that n is any variable perpendicular to the surface. Now here that is Z. That's why you can just take this one. So sigma is equal to minus epsilon naught into, let me just rearrange. So dou V above by dou n, dou Z. Okay, this is above. And these derivative are taken on the surface. Remember, we have taken some small thickness, then we made that one 0, am I right? At Z equal to 0. And this below part is 0. So use this one to find, take derivative with respect to Z, put Z equal to 0 and find surface charge density. Is that okay? So he has given that calculation, do that one, induced surface charge. And try to solve problem number 3.7. 3.7. Problem number. Don't lag here, okay? Because I'll go a little more fast again tomorrow. Don't lag here. Finish out homework. Yeah, what is that question? In the surface, on the surface. Yeah, total charge since it is infinite in extent, suppose negative charges are here, maybe positive charges are at the infinite boundary. You can imagine like that. Or it is little difficult, it's little conceptual to talk about that one, am I right? Charge on the surface. Again, one more thing that he hasn't mentioned is whether it is initially neutral, whether it is initially uncharged or charged. Net charge initially 0 or not. He will not talk about that. Is that okay? So now what would happen here is, my idea is, look at here, if there is plus q charge, there will be induction of minus q charges on the surface, so that all electric field will start from this one, they will end on the surface. There will be no field here. Now look at here, now look at here. If you take this configuration, there are field above as well as below. That's why I am saying this configuration is not equivalent below the plane. Above the plane it is equivalent. Can you just see that one? Above the xy plane, both configurations are equivalent. Below the plane, that image configuration is not equivalent to this one. So that's why this problem will come while finding the electrostatic energy stored. Electrostatic energy stored here, that will be double that of this one. You can see that one. Why? While taking this one, we are taking our entire region, E square d2, am I right? Integral of E square d2. So that we will find double of that one. You have to divide by 2 forcibly to get what is the electrostatic energy here. Is that okay? We shall take that idea, okay? We shall extend that idea in the evening. Is that okay? So, but try to just have some basics about this one. Again, finish out all problem from the last chapter. And again, within 1 or 2 classes, I have to finish this chapter, okay? Yeah, so let us, yeah. Here. No, whatever the work here you do, or just think of electric field. Integral of E square d2. Don't think of moving the charges. That formula also gives the same answer, isn't it? Now look at here. What is the difference between these two? This contains electric field in both regions, above the plane as well as below the plane. This contains electric field only above the plane. So just read out the next one. Finding the force, and force you can find using image problem. Force on this one, force on this charge, you can find using image charge. But work done, you can't find by that one, because while having this configuration, you have to move both charges. But while having this configuration, you have to move only these charges. These charges, these image charges, they will move freely because there is zero potential. Okay, no work is needed to move the charge on the zero potential plane. Okay, he will explain that one later. Okay, read out very carefully and try to do that one. Okay, try to find force also after finding surface charge density. So try to find force on this one, try to find work done. If you use this configuration to find the work done, or if you use this configuration to find total electrostatic energy stored, that will be definitely double that of this one. And that will be wrong because our interest is to solve this problem, isn't it? And we have to divide that one by 2. Okay, and along with that one, do that outside problem. Okay, so we shall discuss 45 minutes particle physics, 45 minutes electrodynamics in the evening. Okay, so 5:45 or 6 o'clock, exactly 6 o'clock. Okay, in the evening. Afternoon 2:30 to 3:30. Anyway,